on the slide. We will first of all cover the basic understanding of the correlation, including autocorrelation and cross-correlation. We will look at the computation of correlation, how is it performed, and what is normalized correlation. And lastly, we will look at one application of correlation. So as I mentioned, these are the contents for our lecture today. So by definition, correlation is a mathematical operation which is used to measure the degree of similarity between two signals. So correlation is, in a grammatical sense as well, gives you a sense of similarity. It gives you an understanding how two objects or entities or phenomena are similar to each other. So in a very similar fashion, this correlation in signal processing refers to a mathematical operation which is used to measure the degree of similarity between two signals, and by that we mean that for example, the signals on one side can be identical, so they can be absolutely similar, or the signals can be completely dissimilar, which is zero in that sense, zero correlation, or they can be similar in an inverted format, like a sine wave with another sine wave of 180-degree phase shift. So these two signals will be dissimilar in an inverted form. So in that case, the correlation will be negative maximum. So there are two types of correlation. One is autocorrelation, which is between the signal with itself, and there is cross correlation, which is the correlation between two different signals. There is a slight essentially they are similar. There is a slight difference in the formula and properties. So let's start by looking at cross correlation. So for cross correlation, we consider two signals, xn and yn, and we try to find out the correlation between x and y. So r is a variable with which we denote correlation. So r, x, y, and this L refers to the lag, to the shift. So you will understand this in a bit. Let's look at the formula. So it's very similar to what convolution formula looks like, except that in convolution there was a need of using a dummy variable and there was a folding involved. Here in correlation there is no folding involved. We have a signal xn and we have another signal yn, which we shift by L units, and L, as you can see, is a lag which is 0, 1, 2, 3 in the positive direction as well as in the negative direction. So what we do is very much like in convolution, we keep the signal xn as fixed and we delay the signal y with various values of L, and then keep on multiplying these two versions of the signal and add them up. So you can very easily see if the values of x and the value of yn minus L overlap more and they have similar numbers, then this expression gives you a very high number, so indicating a very high correlation. And if, for example, there is very little overlap or the numbers are dissimilar, then the correlation gets to a low number, indicating a low similarity. So not only the correlation gives you a similarity of the signals as it is, but it also gives you the correlation at different values of lag. That it is possible that there are two signals. One signal is starting at 0 and the other signal is starting at 3, but is essentially the very same signal as the original one. So in that case, when we do the correlation, the correlation will find that the highest similarity is occurring when you shift the original signal by 3 units. So that is the essence of correlation, that it gives you the correlation degree of similarity, as well as the points where the correlations are maximum or minimum. And this second formula is essentially the same thing, saying in a written in a different format. Here we were saying that we are fixing x and delaying y. In this formula we are fixing y and advancing x. So essentially the both formulas are talking about the same thing. Now let's look at the cross correlation between y and x, because we have changed the reference. Previously we were looking at the correlation of x with respect to y, and now we are looking at the correlation of y with respect to x. So ryx will be y of n, x of n minus 1. So the places of the signal get reversed, and ryx of L can also be said as to fix x and advance y. Obviously it is easy to see through this computation that if we compute rxy and then we compute ryx, then basically the results will be same, except that these results will be a folded version of one another. It's very easy to see that if in the formula of ryx of L we replace L by minus L, then yn remains yn, but x of n minus L becomes x of n plus L. So yn into xn plus L, this is a formula for rxy. So here you see that rxy of L is basically a folded version of ryx. So this is important because if you already know the convolution in one direction, then you do not have to compute the correlation in one direction. Then you do not have to calculate the correlation in other direction. You just simply fold the signal, and this will be the correlation of the other relation. Similarly, if you want to find out the relation between correlation and convolution, it is another simple relation, as I mentioned in the beginning, that if you look closely at the formula of correlation and convolution, the only difference is that in convolution there is a folding of one signal involved, whereas in correlation there is no folding. You just simply go on with the shift and multiply operations. Now if we want to find out correlation using convolution formula, then what we can do is just fold the signal, one of the signals once, and then perform the convolution. So what will happen that you have already you fold the signal once, and then when we apply convolution, the convolution formula again will perform one fold. So essentially when you perform two folds on a signal, you get back the original signal, and that's how you get back the origin correlation function. And the simple mathematical proof is defined in these two steps, where we have convolved xn with y of minus n, and the simplification performs and provides us back the convolution formula, correlation formula. So this shows that the convolution between a signal xn and its another signal y of minus n gives us the correlation. Right, so now let's look at autocorrelation. It's the same as cross correlation, except the signals are the same. So we are correlating x with x of n minus L, and essentially the rxx, whether you go in one direction or the other direction, will give you the same answers. Now let's look at the cross correlation example, and this is between two signals xn and yn. And once we are done, we will also have to look at the correlation of yn and xn. This you can do on your own to prove that the results are the folded version of one another. The signals are 1 2 3 4 5 and 5 4 3 2 1, and the origin is at 3. So as we mentioned in the formula, that we have a signal xn and we have a signal yn. and this